All right, welcome to our first lesson for our first unit. I will try to cover all the details, but not ramble too much. Let's start our first lesson, the historical timeline of our atomic theory. Okay, so if you ever played the game Minecraft before, we know that the basic building block of the Minecraft world is with those wood block, dirt block, or sand block, right? So same thing for our universe. There must be something that builds up our world too. So scientists have discovered or worked on atomic theory for a long time. The first idea of an atom actually came from an ancient Greek philosopher about 2,500 years ago. So he's known as the laughing philosopher. So he did a thought experiment. So one day he was just thinking, if you grab any kind of material and break it in half and in half and in half again until infinity, can you do it forever? And his thought experiment was, no, you can't, because eventually you will encounter something that is so small you cannot cut it in half anymore. So any material that can be broken in half, eventually it cannot be broken down anymore. So he called it atomos. So A means not or anti, right? So is like symmetrical is symmetrical. Asymmetrical is not symmetrical. So A is like no. And then tomos means cut. So atomos literally translates to indivisible or uncuttable. Okay, so that's he came up with this word, and then according to Democritus, he said matter is made of tiny particles. These particles cannot be divided or cut any further, and then different materials are made of different kind of atoms. So for example, he thought water droplet, if you keep on breaking it in half and in half and in half again, you're gonna get to a water blob that cannot be cut anymore. That's the water atom. And then a piece of metal probably have little hooks because metals don't break when you bend them. They can bend and they don't break. So he was like, there must be something that's connecting the metal atoms together. So it was like all imaginary, all just a mind thought. So there was no experimental data or evidence to back up his reasoning. So most people didn't buy his story or theory. So after Democritus died, another famous philosopher, Aristotle, he disagreed with Democritus. He said elements can be divided forever. Our universe is made of four basic continuous elements, that is earth, water, air, and fire. So every single year I jokingly say to my students that he's the original Avatar, right? Because Avatar have all four elements. But yeah, because he was more influential, his idea dominated more and causing most people to ignore Democritus's idea of an atom. So here you can see right here we got Terra, that's earth, we got water, air, and then fire. So that's his idea, Aristotle's idea. But he was wrong about it, even though he was a great philosopher. And then in the early 1800s, 1803, scientist John Dalton, if you look into his story, how he discovered or proposed his atomic theory, is pretty interesting. He basically studied different types of gas and then proportions and stuff like that. But his conclusion was that all matters are made of atoms. Atoms cannot be created or destroyed. Atoms of the same elements are identical, and then atoms of different elements are different. And compounds will form when atoms combine in whole number ratios. So right here you can see Element of oxygen will just stay as oxygen. Elements of nitrogen will stay as nitrogen. They cannot interchange. So different elements or different atoms are different. And then atoms cannot be created or destroyed. And then during a chemical reaction, it's just different combinations. So let's say nitrogen combines with oxygen, and then you make a new compound. So that was his theory. Okay, he got something right, and then he also got something wrong. So what he got right was matter is indeed made of atoms, and then atoms combine to form compounds, and chemical reaction is basically a rearrangement of atoms. But he was also wrong about atoms cannot be divided anymore. Actually, later on, we've learned that atoms can be divided into smaller particles, or they are cuttable. That's basically a nuclear reaction, right? And then atoms of the same elements are not always the same, because later in this unit, we're gonna learn about isotopes. So the same element or same type of atom can be different. So, but for more than 200 years ago, his first initial modern scientific atomic theory was pretty amazing, right? He got most parts right, but he had no idea about the existence of nucleus, the existence of protons, neutrons, and electrons, stuff like that. So his atomic theory was known as the solid sphere model. So all he thought atom is just a round sphere that has nothing in there. It's just little round balls that makes the whole universe. Okay, that's the solid sphere model. And then in the late 1800s, scientists began to experiment with electricity. J.J. Thomson used a device called the cathode ray tube. And this is a very famous experiment, the cathode ray tube experiment. So basically, have you heard about the story about Benjamin Franklin? He was flying a kite in the rain to capture electricity. So that was happening in the 1700s. So scientists has been exploring or experimenting with electricity for a while now. So by the late 1800s, we have the cathode ray tube. So basically, before we have all LED or LED flat screen TVs, our televisions or TVs are really big and bulky, and because we have to house a giant cathode ray tube in there to provide images. Okay, so J.J. Thomson tried different metals, and then he discovered, something. They all behave the same. So he was able to bend the beam inside the cathode ray tube with a magnet. So Thomson's finding proved that there are smaller particles than atoms, and all matters contains those particles. So basically, J.J. Thomson discovered the first subatomic particle. So sub means below. So subatomic means below or smaller than or under, right? So sub and subway is train underground. So sub is smaller than, and then atomic, atoms. So there are particles smaller than an atom. And the first one that was discovered was electrons. So we know that electrons have negative charge. So what J.J. Thomson discovered was the ratio of electron charge over mass, the mass of electrons. But he didn't know how much charge those electrons carried, and he didn't know how heavy those electrons were. But he just know there are negatively charged particles. Okay? And this is J.J. Thomson's atomic model. So remember our first atomic model, it was just a solid sphere. And now we know that there are actually tiny electrons all over this solid sphere. So this is the new model called the plum pudding model, because the plum pudding have raisins in them. So that's like the little negative electrons, and then the whole pudding are positively charged sphere. So he didn't know about protons. Protons wasn't discovered yet. So because atoms are all neutrally charged, he said, well, if there are negatively charged particles in an atom and the whole atom is neutral, then there must be positively charged. They must be in a positively charged environment. So that's the sphere. But he didn't know anything about protons yet. So this is atomic model for J.J. Thomson, the upgraded one with electrons in there. Interesting fact is Thomson won a Nobel Prize for discovery of electrons as particles, and then his son Thomson also won another Nobel Prize for discovering electrons as waves. So we have the wave-particle duality. So that's later on you might learn that in physics, but for chemistry, we just need to know that this is the second atomic model, the plum pudding model. Okay. So to calculate or to find the charge or the mass of electron, another really brilliant scientist, his name is Millikan, he designed this experiment where little tiny oil droplets was being sprayed by this atomizer. So this atomizer pretty much just sprays oil into really tiny particles, and then with gravity, the particles will fall into a hole right here, and then there's two plates. We got a positively charged plate and a negatively charged plate, and there's a viewing microscope. So what happens is he can dial or control the voltage of this negatively charged plate until the tiny oil droplets suspend or hover in midair. Okay, and he can calculate the amount of charge in those tiny particles. And what he found was they all come in multiples of the same tiny value. And he calculated the charge of electrons. So that was a really brilliant experiment. It's called the oil drop experiment. Okay, and by plugging in the electron charge of the electrons into J.J. Thomson's discovery of the ratio to the mass, we were able to calculate the mass of electrons, which is 9.11 times 10 to the negative 31 kilograms, which is really, really tiny. So electrons almost weighs nothing. So compared to an atom, okay? So that's that. And then our next experiment was by Ernest Rutherford. So Rutherford actually worked under J.J. Thomson. So Rutherford was J.J. Thomson's student. They worked in the same lab. So he said if J.J. Thomson's finding was correct and his atomic model is correct, he wanted to test it. So according to Thomson's model, if you shoot alpha particles, so again, scientists at that time have already have a pretty good understanding of radiation. So there's three different types of particles. We got gamma, alpha, and beta particles, right? So alpha particles are positively charged. So Rutherford basically said, if we shoot alpha particles through atoms, it should probably go straight through, right? If everything is evenly distributed. And there's electrons almost weigh nothing, right? Nothing should be interfering with alpha particles going through. So he designed an experiment to called the gold foil experiment, to shoot alpha particles through a really, really thin piece of gold foil and then counted how many where the dot landed. So he was expecting all the dots to go straight through, but what he found surprising was that some of the alpha particles was actually deflected into different areas or different angles, and some even bounced back. So he was really shocked by this observation. So in Rutherford's model, he said, well, there must be a really concentrated, positively charged particle in a tiny nucleus that's blocking alpha particles, that's deflecting it, okay? So this is the animation of what could be happening. So that's Rutherford's assumption or conclusion. He said most atoms are just empty space. Positive charge is concentrated in a nucleus, and then nearly all mass is located in the nucleus, and electrons exist outside of the nucleus. And because the whole thing about this is a nucleus, his model is known as the nuclear model, okay? So this is our third atomic model. So let's look at a Bill Nye video.
Take a look at this. It's our proper proportion giant atom model of science. Now, this part isn't very giant. That's because it's just the nucleus, the middle of an atom. Now, in here are two kinds of particles, protons and neutrons. No one knows what they would really look like. The protons have a positive electrical charge, like a spark, and the neutrons have no charge. They're neutral. They just hang out in the nucleus. Now, buzzing around the outside of the nucleus are very small particles called electrons. Maybe you've heard of them. In fact, the flow of electrons from one atom to another is called electricity. If this vibrating, buzzing ball is the nucleus of an atom, how far away do you think the electron would be? Well, as far as you could jump? No. As far as you could throw a ball? As far as you could run? Well, yeah. Take a look. You can see it from here. It's way out there. The electron would be here. 500 meters, 5 soccer fields from the nucleus. So, everything that's made of atoms, everything that you can touch and feel, is mostly empty space. Empty space. Empty space. Empty space! Now, the electron weighs, a 10,000th of those particles in the middle. And it's going around so fast that it's only here now and then. It's here, and then here, and then I gotta go.
Okay, so you realize how the LED dots that represented an electron in the Bill Nye video was buzzing, like flashing, right? That's like the uncertainty principle. The electrons are always just kind of teleporting. We don't know where it is, or we don't know their the direction or their movement or momentum. So that's college level chemistry. Is really confusing. I don't have a good way to explain it right now. But our next model, but keep in mind, during Rutherford's atomic model, he didn't know about protons. Okay, so after he proposed his idea or his atomic theory, scientists studied the nucleus and they realized that the nucleus contains a positively charged particle in there. And that's our second subatomic particles being discovered. They're called the protons. So now we have two subatomic particles. The first one is electrons. E-L-E-C-T-R-O-N. And then the second one is protons. Okay, electrons are negative, protons are positive. So we know with a magnet, positive and negative charges, opposites attract, right? So if we have a positive nucleus in the center and the electrons are just on the outside, how can we have an atom that's just mostly empty space, right? So he said, Rutherford's model said the atom is mostly empty space. Why? Wouldn't all the negative charge just get attracted to the protons or the charges at the nucleus, and they all just combine into like that, and then the atoms are really tiny instead of having mostly empty space? So to solve this problem, our next atomic model or scientist, you can see Einstein in the background. So they were working on the Manhattan Project in this photo. So right here, there's a major flaw in the nuclear model where electrons should not exist outside in a huge empty space if it's what Rutherford stated. So Niels Bohr, he basically used quantum mechanics to calculate there must what is that spectra emission things to explain this. So electrons can only occupy certain places inside the atom, and he called those energy levels. So you see these circles right here around the nucleus. These circles are the energy levels or electron shells that Bohr is trying to explain. So when electrons go from one circle or one energy level to another one, if it goes to a higher energy level, it will gain energy. It needs energy to go to a higher level, okay? And then if it goes down to a lower energy level, it would release energy. That's why we see those spectral emissions, right? So that's why fireworks have different colors, because the electrons are going up and down into different energy levels. So that's Bohr's model. Bohr's model basically proposed the energy level and explained how electrons are not collapsing into the nucleus. All right. So the Bohr model is also known as the planetary model because it kind of looks like little planets surrounding our sun, like our planetary or solar system. So it's also called the planetary model. But Bohr model is the main atomic model we're going to study in high school because it's a really good visual to understand the basics of atoms. Okay, but there is a newer model is also up to this point we only know there are electrons and protons, right? But there's a third subatomic particle called the neutrons. The problem with neutrons is that this particle has no charge. It's really tricky. It's like a ghost. So when you weigh the atom, you only get you would expect certain amount of protons and electrons, yes, but their mass is much heavier than just the protons and electrons. So scientists was like, what is contributing to this weight? So Chadwick is the person that did experiments and then find, oh, there's neutrons in there. So his work is very important. It helped us understand atomic mass and how nuclear reactions work, right? So that's why he's the only English scientist with full access to the documents in the Manhattan Project. So nuclear bomb wouldn't be a reality without the discovery or understanding of neutrons. So our last atomic model is quantum model. Okay, you know what? Let me do a little summary here. So now we have 3 subatomic particles. We got subatomic particles. We got Number 1 is electrons. And then number 2 was protons. And then number 3 is neutrons. That's the sequence of the discovery. Electrons first, and then protons, and then neutrons. Okay, that's the 3 fundamental subatomic particles that builds up an atom. And there are even smaller particles that's smaller than these 3, like quarks and stuff like that, but we won't get to it in high school chemistry. So our last atomic model is called the quantum model. So Erwin Schrödinger, this guy, really smart dude, he basically said that electrons actually doesn't just orbit around the atom like what Bohr said. It's actually more like a probability cloud. So the darker or denser color of the quantum model will just indicates the higher probability of existence for the electrons. So this one is a little tricky or difficult to understand, but just know that this is the most modern or widely accepted atomic theory up to now. So this is still the atomic theory of today. I think this was back in 1920 or 30 something. Okay, so that's the atomic model of modern days. But we're going to study mostly the Bohr model because this one is very clear. It helps us understand the properties of atoms pretty easily. And yeah, it doesn't get into all that mathematical stuff. So here we have the atomic structure. Electrons are negatively charged. They're outside of the nucleus, mostly just empty space. Protons are positively charged. They are all concentrated in a tiny nucleus in the center. Neutrons have no charge, and they're also inside the nucleus. Okay, so protons and neutrons are inside the nucleus. Electrons are outside the nucleus. So remember, electrons, they're really light. Their weight is almost negligible. We can ignore the weight of electrons. So most of the mass is inside the nucleus. Okay. So let's look at this. Oh, this meme right here. So electron and neutron are hanging around, and then electron is attracted to protons. So remember, electrons is attracted to protons because protons are positive, and then electrons are negative. Okay, so positives and negatives attract. Next one, this one, proton and neutron, they're making out, and then electron over here is just watching, right? So again, atom is mostly empty space. You see how far they are. Protons and neutrons are inside the nucleus. They're at the center, and the electrons are far away. Okay, so that's pretty much everything you need to remember. The historical timeline is right here. The atomos idea came from Democritus, which is long time ago. And then solid sphere came from John Dalton. And then that's the first atomic theory, modern days. He thought it was just a round circle. And then J.J. Thomson bent the light in the cathode ray tube and discovered there are electrons. And then the whole sphere is positively charged. So he didn't know about protons at that time. And the nuclear model, he said, oh, there's a positively charged nucleus in the center, and then the electrons are on the outside. And then Bohr is the one that proposed the different energy levels and the planetary model. You can call this planetary model or the Bohr model. And then the last one is quantum model. So the quantum model, we don't really get into details about this one, but you see, it's supposed to be clouds, right? The picture that I showed you, but you see those little circles and things right here. We're going to get into a little bit of this in the future lessons for when we learn about electron configuration. Okay, but for now, let's just this quantum model is the modern one, and then we're going to study mostly on Bohr's model, and then we only use the quantum model when we learn about electron configurations. Okay, and make sure you know all of these atomic models. Science is a process that evolves with new evidence. So whenever somebody make a new discovery, the theory will update itself. So nobody is a genius that knows everything. It all builds on top of previous work. So each scientist is building or adding new details or evidence onto the work from other scientists. So we all work together. Okay, so hence the famous quote from Isaac Newton. He said, "If I have seen further, it's because it is by standing on the shoulders of giants." Okay, so yeah, science is a process that keeps on evolving. So maybe in the future, the quantum model will be outdated and we discover something new, and that could be you, right? So, yep, this is our lesson about the atomic theory.